Hello, and I'm happy we are back with the next section of our course. And I bring today is a puzzle. It's kind of a math puzzle, but you don't need to do a lot of calculations. It's kind of a riddle. Add one line to make it fine. There's a way that you see the equation here: 5 plus 5 plus 5 plus 5 equals 555. And this is wrong. This is completely wrong. There are two ways of solving this problem adding one line. One way, let me say, is just making this different. Yeah, but it's not what I'm looking for. It's not what you're looking for. There's another way. You can add this line somewhere else and you make the equation fine. How would you do this? And later we will get back to this puzzle after our lesson, because today we're going to work on chapter 7, Rational Exponents, Radicals and Complex Numbers, section 7.2, Rational Exponents. The objective A is to understand the meaning of A exponent 1 over n. If n is a positive integer greater than 1, and nth root of A is a real number, then you can write A, you can make A exponent 1 over n equals the nth root of A, right? When you have an exponent like this, with the 1 over n is equivalent, is the same thing as the nth root of A. And let's work on a few examples to understand how to work with this kind of expression. Okay, with this kind of notation. Sorry, with this kind of notation. Use the radical notation to rewrite each expression, simplify if possible. So letter A, 81 exponent 1 over 4, as we have seen before. We can rewrite this as fourth root of 81, right? And if you solve it, the fourth root of 81 is equals to 3. Now the next thing, letter B, 64 exponent 1 over 3 is the cube root of 64, and we know that the cube root of 64 is going to be 4. And if you have x exponent 1 over 4, you just write this is the fourth root of x. This is how we work with this notation. We can write as a root using the root notation, or using the exponent of 1 over n notation. Another examples, check this. Simplify if possible. Negative 16 exponent 1 over 2, and you have to pay attention because the exponent is only 16 is submitted to exponent 1 over 2. It's like you have negative and then only 16 is submitted to exponent 1 over 2. That means this negative sign, when you represent as a root, is going to be in front of the root, not inside of the root. Square root of 16 is negative 4. Okay? Now, 32x exponent 10 over 1 over 5. That means we can apply here properties of exponents. We're going to see it a bit later, but we can write as 32 exponent 1 over 5 times x 10 exponent 1 over 5. This 32 exponent 1 over 5 is the fifth root of 32. And x exponent 10, we can write x10 times 1 over 5. And this is equals to, let me write here at the bottom, equals to, the fifth root of 32 is 2, right? And the 10 exponent 10 times 1 over 5 is 10 times 1, 10, divided by 5, 2, x squared. Okay. The next example, letter F, we have parentheses 16 times x exponent 7, exponent 1 over 3. And we can rewrite this as the cube root, right, of 16x exponent 7. These cube roots we can break down 16x exponent 7 as 16 is 2 exponent 7 times x exponent 7. 2 exponent 4 times x exponent 7, right? And we can also write this. We're going to see properties of exponents later. We can write this as, let me write here at the bottom, cube root of 2 exponent 3 times 2. This is to the fourth, and x exponent 3 times x exponent 3 times x. This will be x exponent 7. Just for you, so you can understand. Those that have the same exponent, the same number, the index, we can bring it outside the root, right? So we will have 2 times x cube root, and inside the cube root we will keep with at least 2 and x, right? This x times x is x squared. Let me write here as x squared. And the answer to this last example, letter F, is 2 times x squared times cube root of 2x. We will we will work later with more of this kind of thing, more of this kind of breaking down and simplification when we see properties of exponents, okay? Now, the next objective number 2, understanding the meaning of a exponent m over n. And if m and n are positive integers greater than 1, with m over n in simplest form, then we can say that a m over n equals the n root of a exponent m. Okay. We can also write this as the n root of a and the whole thing exponent m. It's all the same thing. We can use one kind of notation or the other kind of notation. It depends on the situation. This will help you solve the problem, as long as the nth root of a is a real number. A few examples. Use radical notation to rewrite each expression. Simplify if possible. So let's write this letter a, example a. We have 4 exponent 3 over 2. So the denominator will become the index. So this is a square, right? Square root. Here 4. And the numerator will become the exponent. it will be something like that, and you can write as this. The same thing, and this will be helpful because we can solve first this situation is square root of 4, which is square root of 4 is 2. Now we use the exponent 2 exponent 3, 2 cubed equals 8. Okay? Now let's check the next one, and we have negative 8 exponent 4 over 3. Remember, this negative is not submitted to the exponent, so we will have negative, and let's use this. The denominator will be the index of the root, and the numerator will be the exponent, like this. So we will have negative cube root of 8 is 2, and 2 exponent 4 is negative 16, right? Now check this expression. We will have 3x plus 7, and we can write this as a root, and the denominator is 3, that means it's going to be a cube root, and the numerator is 7, so 7 is the exponent. We can simplify as we have seen before. We can rewrite this. Let me write here 3x plus 7 exponent 3 times 3x plus 7 exponent 3 times 3x plus 7. This is just for you to understand, because you can do it in a simpler way, that you can see, you can understand that this we can remove from the roots, right? This we can simplify, we can remove from the roots, and then we will have, let me use this space, 3x plus 7 is squared times cube root of 3x plus 7. Okay, this is the answer. Okay, now let's move on to the next objective number 3, to understand the meaning of a exponent negative m over n. And now, to complete the definitions, we want to include negative rational exponents. And if a exponent negative m over n is a non-zero real number, then you can say that a exponent negative m over n equals 1 over a exponent m over n. You can write like this, and you already know how to rewrite this one as a root, using the nth root and the m as exponent, right? So let's work on a few examples and try to understand how to use the different forms. 64 exponent negative 2 over 3, we can rewrite as 1 over 64 exponent 2, exponent 2 over 3. Okay, this denominator we can write as 1, and we have seen this before, right? Check the exponent 2 over 3. The denominator of the exponent is the index of the root, and the numerator of the exponent is the exponent, like this. And cube root of 64 we know is 4. And this is 1 over 16. Now let's try the next one. Letter B, negative 16, exponent negative 5 over 4. And the negative is here is not submitted to exponents, so we have 1 over 16 exponent 5 over 4. Okay, and now this denominator here we can rewrite. We can use the notation. The denominator 4 is the 4th root, right? And the numerator 5, it becomes the exponent. Cool? The 4th root of 16, this is equals to, the 4th root of 16 is 2, and 2 exponent 5 is 32. The answer here is negative 1 over 32. Great, now objective number 4, use rules for exponents to simplify expressions. So these rules or properties of exponents we can apply to simplify and the expressions we have seen at the beginning, and a few examples. I told you that we will see this later, and that's it. This is what we're gonna use to simplify if we have expressions with exponents. The product rule for exponents. If you have a product, then you're gonna add the exponents. Power rule for exponents. If you have am and then exponent n, you're gonna multiply. Power rule for products and quotients, and check this. And this looks like a distributive property. I like to say you're going to distribute n into each one of the factors. And quotient rule for exponents. If you have this kind of thing, a exponent m over a exponent n, you can subtract the exponents. 0, if you have any thing that a base with exponent 0, this is going to be equals to 1 as long as a is different from 0. And negative exponent, we have seen somehow have seen before. If you have a exponent negative n, it is equals to 1 over a exponent n. Well, this is something that you don't need to memorize. You need to have like your formula sheet and in somewhere available, somewhere you know where to find, and whenever you need, check this and use these rules to simplify expressions that have exponents. Let's work on a few examples. Use properties of exponents to simplify. And check this, it's a multiplication. We have x exponent 1 over 2 times x exponent 1 over 3. Let's go back a little bit on the rules and find what kind of rule can we apply. And I think we can apply this one, right? The multiplication product rule for exponents. We will add the exponents because they have the same base. We will add, that means this is x exponent 1 over 2 plus 1 over 3. And how do we add fractions? We need to find the least common denominator. It's going to be 6, and then the first numerator is 3. The second numerator is 2. This is equals x exponent 5 over 6. We can also represent this is the answer, this is the result. But remember that we can also represent this using the root and exponent notation. The denominator here is going to be the index of the root, and the numerator is the exponent, right? We've seen before. So this is the answer. Now, check this. 7 exponent 1 over 3 over 7 exponent 4 over 3. Check the rules. And what can we apply? Definitely this rule here. Can you see? This is the quotient for exponents. And then we need to subtract the exponents. This is equals 7, 1 over 3 minus 4 over 3, right? And this is 7, 1 over 3 minus 4 over 3, negative 3 over 3. And what's 3 over 3? 1, right? 7 negative 1. 7 negative 1 is 1 over 7. And finally, let us see, we have, what about this? We have the same base, y, and a multiplication with exponents. We have to do kind of the same thing with did with letter A. We will add the exponents. So negative 4 over 7 plus 6 over 7. This is going to be equal y exponents. Negative 4 over 7 plus 6 over 7 is 6 minus 4, 2. 2 over 7, right? And that is the answer. This is the answer. Now letter D. And we have here 32, parentheses, 32 exponent 1 over 5 times x exponent 2 over 3 with this parenthesis, the whole thing exponent 3 cubed. So the first thing you can apply, let's go back to the rules and check this. We can apply something like that. This is the power rules for products and quotients. We can apply this, and we will multiply this n by each one of the exponents for each factors. So we have 32, 1, 5, exponent 3 times x, 2 over 3, exponent 3. Now we get this one, right? So we're going to multiply 32, 3 over 5 times x, 2 times 3, 6 over 3. Well, 32 exponent 3 over 5, this is, remember, 5 root of 32. Let me fix this. 32, this exponent 3 times 6 divided by 3, 2. So times x squared. We can find the fifth root of 32 is going to be equals to 2. 2 exponent 3, or 2 cubed, is 8x squared. Okay, now I just cleaned up the screen. We have more space to work. And let's work on the next, letter E. A exponent 1 over 4 times a negative exponent negative 1 over 2 divided by a exponent negative 2 over 3. Look, if check the properties, we will apply this. If they are multiplying, we're gonna add the exponents, and we will also apply this. If they are in a fraction, they are dividing, we subtract the exponents. Okay, so A, this one, 1 over 4, we will add to negative 1 over 2. So add negative 1 plus negative 1 over 2 is negative 1 over 2 minus 1 over 2. And this exponent here at the bottom, 2 over 3, we will subtract from the ones here at the top. Apply, we will add fractions, so we need to find the least common denominator, which we have denominators 4, 2, and 3. It's going to be 12, the denominator. And for the first fraction, the numerator is 12 divided by 4, 3, 3. 12 divided by 2, 6, 6. 12 divided by 3, 4, times 2, 8. The exponent will be 3 minus 6, negative 3, minus 8, negative 11. Negative 11 over 12. And if I have a negative exponent, we can write like the inverse, 1 over A exponent 11. A exponent 11 over 12. Okay. This is the right answer. This is the answer that we're looking for letter E. Now, moving to the next objective, number 5, use rational exponents to simplify radical expressions. And check now we know how to change from radical exponents to fractions as an exponent. So we can move from one to the other in order to be able to simplify, to use some kind of properties of fractions to simplify rational expressions. So if you have radical expressions, you can transform, you can change into a rational exponent to help you simplify it, like we have here. This, the 8th root of x exponent 4, we can write as a rational exponent, right? We can write as x, and the numerator is going to be the exponent, the denominator is going to be the index of the root. And look how interesting, because I have 4 over 8 is something that you can simplify. You can write as 1 over 2, right? You can write the equivalent fraction 1 over 2. This is square root of x. So writing as a rational exponent helped us to simplify the radical expression. Now another example. Let's say this. We have 6th root of 25, but we can write 25 as 5 squared, right? 5 squared is 25, and this is 6th root. And we can write this as a rational exponent 2 over x, right? The numerator is the exponent, the denominator is the index of the root. So we have 1 divided by 2 over 6 is the same as 1 over 3. 1 over 3. And this is cube root of 5. Another examples here to apply rational exponents and write as a single radical expression. Let's check how to work this out. Let me split this. We can write first this one, the square root of x, we can write as x 1 over 2, right? Times. And the fourth root of x is x 1 over 4. But we know by the rules of exponents that if we have the same base, we are multiplying the factors the same base, we can add the exponents. So is x 1 over 2 plus 1 over 4. And this is equals x. And we have the least common denominator 4. 2 plus 1. This is equals to x 3 over 4. Okay. And you can write this as the denominator is the index of the root and the numerator is the exponent. This is the answer. You can simplify, and before you had two roots, right? Two separate roots, and you can represent all in one unique root. Well, I just cleaned the screen because I will need more space. And for letter B, we will try to put them together in just one root, right? So we can rewrite the cube root of 5 is 5 exponent 1 over 3 times the square root of 2 is 5 exponent 1 over 2. Okay? And find the least common denominator of this denominators 3 and 2, and we can rewrite this as 5 exponent. The least common denominator is going to be 6. 5 exponents. The equivalent to 1 over 3 is 2 over 6, right? Times, and the equivalent of 1 over 2 is 3 over 6. Now we can rewrite this as 5, and the exponent is the numerator, 2, 1 over 6, exponent 1 over 6, times, and 2, the exponent is 3, and the rational exponent 1 over 6. Check this, we have the same radical exponents, and we can put this in only under one root. It's going to be the 6th root, right? So this is equals 6th root of 5 squared times 2 cubed, and 5 squared is 10, is 25, I mean 25, and 2 cubed is 8, and we have the answer, 6, the 6th root of 25 times 8, 200. That is the answer that we are looking for. Have both terms now are under the same root, and we have just one number with the same 6th root. Well, this is the end. We finished now the section 7.2. Check the puzzle, and this is kind of a silly puzzle. And let me tell you, I told you you can write the line here and this will become true because they are different, but what we are looking for a different kind of solution, a more creative. And if you think maybe we can move the line instead of using the line to make the different symbol, we can use the same line here. Check it out. And we will transform the one positive sign into number 4 just by adding one line. And now we have 545 plus 5 plus 5 equals 555, and this is true. Now it is true. This is the answer. This is the line that you have to add to make it fine. Thank you for watching the video, and see you soon on the next section of our course.